Spring forces for when the grass turns green. No, we're not talking about springtime. We are talking about actual boing, 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 springy springs. If you actually remember, way back earlier in the year, we did a spring lab. We took a little spring. You picked your spring. We attached it to a pendulum clamp, and then we put masses on the spring as it stretched out. And when we did this, we actually created two graphs. We created a length of stretch based off of the amount of weight you put on the spring, so some amount of force, and then we did a different graph where you put some, we just exchanged these axes, okay? It was an exchanged axis graph, so we just swapped these and created this over here. And whenever you did this, you plotted some points here, you know, and it looked something kind of like that in theory, and we got a slope from this graph, and this slope we said was the spring constant, and that spring constant we gave it a variable k, and we actually ended up creating a little equation at the end of that which said that F equals kx, where the amount of force from your spring is equal to the spring constant, and instead of using L for a length, we use X because we've been using X for displacement this whole year. So it's how strong your string is, or your spring is, and how far you've stretched it out. That's the amount of force. And we saw that like week one. It was like a week one lab, one of the first labs we did. But guess what? We're going to use that equation now, because that is a spring force, and it's a force specific to springs and some other restoring objects. So we're going to tie it in right now, because that spring force can be related to F equals ma. So we've been doing F equals ma technically since like week one, even though I haven't really told you. There is a weird thing with springs that we need to be aware of. Some people look at it differently depending on how they set up their springs, but technically when you look at a spring equation, there is a negative in front of the k and the x. And the reason why there is a negative there is because springs are a restoring force. If you have a spring and it's originally just sitting like this and you stretch it out, it wants to pull back. It always wants to oppose the direction you pulled it. So if you pulled it in a positive direction, that force wants to pull it back negative. If you pushed it in a negative direction, well, a negative of a negative is a positive, and it wants to push back. So it's a restoring force. It always wants to oppose whatever you've done to it. And that's what that negative means. It's a restoring force there, and if you did include the negative, it would work itself out mathematically, so everything would work. Some people really like that. Some people like including that negative. They like thinking about, oh, you know, I've called this the positive direction of the spring, so it wants to pull back in the negative direction. Some people love that. Some people have a better time where when they set up their free body diagrams, they can say, I don't care about the direction we've called things. I know what direction the spring wants to pull. So they just call their spring force kx, and they use their free body diagrams to give themselves an orientation on should it be a positive value or should it be a negative value. And that's how they go about solving those types of problems. Okay? But in the end, though, we are just using this spring force kx because it is just another force. Just like when we saw friction was fun, just like when we saw weight was equal to mg, spring force is just equal to kx. And we just toss it in an F equals ma equation, and we get the same things as always. So if we kind of look at a problem here, let's imagine for a second, okay, so we can do a problem like this. Let's imagine for a second that we have a wall sitting here, classic physics way of drawing a wall, and then there's a flat kind of surface, a table, a floor, whatever. Attached to the wall is some spring, and attached to that spring is a block. Okay? This block is pulled back from rest, because this is where the spring is just initially sitting with the block, it's pulled back from rest a distance here, a delta x, or an x if you'd like to think about it like that, of, oh, let's say 0.5 meters. Okay. When it is let go, if you imagine letting it go, you know the block's going to snap back like this. But when it's let go, it's going to accelerate at 3 meters per second square in that direction. And let's give the block a simple mass. Let's say its mass is equal to 2 kilograms. What I'd like to know is, what is the spring constant of this spring? Okay, so let's find that. If we think about this, we pull the block back and then we let go. And if this is a nice frictionless surface, which just for the moment, let's assume it's frictionless. If we wanted to include friction, we would just need another force. Fun, friction's fun. But it's frictionless right now. So if we pull the block back, then when we let go, it's going to snap forward. Okay? So I guess the way we're calling this problem is, since this acceleration is going to the left here, and it is positive, I guess that means the left is positive and the right is negative. But if we drew a free body diagram of our block, what we would have is our block would be here, and there's only one force pulling it to that left. There's the spring force. That's it. That's all we have. There's no friction pulling back on it. Since there's no friction and we're on a flat surface, I don't care about the normal or the weight. If there was friction, I would have to care about the normal. If we were on a hill, I would have to care about both of those, because the hill would be causing some effects there. But we're not. We're on flat surface, so the only force that's really causing this direction of motion is this spring force. So if I wanted to set up F equals ma, which is our classic go-to equation, right? We have the net forces, or the sum of all of them, equals ma. Then I would just have to say, hey look, I've got one force. It's Fs. It's positive because it's going to the left. And this is where I was talking about, some people don't like using that idea of the negative kx, because the free body diagram declares whether this should be a positive or negative value. So let's not worry about it. If you are one of those people who likes using the negative, then technically we would have pulled this a negative 0.5 meters, and then the negative of negative 0.5 would make it positive. So it's irrelevant, however you like to do it. What we have down here then is Fs equals ma. We know Fs is equal to kx, or negative kx if that floats your boat. However you like to think about the problem. So we can just put in kx here equals ma. And now it's just a matter of plopping in some numbers and calling it a day. If we do plop in some numbers, well, we don't know what k is, so it's staying as k. That's what we're looking for. But we knew x was 0.5. Like I said, if you had the negative, it'd be 0.5 anyways. So however you'd like to think about that. We said the mass here was 2 kilograms. This is in meters. And we said the acceleration was, what was that acceleration? 3 meters per second squared. So if we want to go ahead and solve this, we know that 2 times 3 is 6, so that's 6 newtons. And then we have k times 0.5. If we divide each side by 0.5, remember, dividing by half is actually like multiplying by 2. So what we're going to get in the end here is we're going to say that k is going to be equal to 12. And our units of a spring force, remember, they are, from our graph that we drew way at the beginning, it is a slope. It is a force per length. So the unit here is a Newton per meter. That's an important thing to remember. So if we go back down for our final answer, our units here are Newton per meter. And we're done. Cool beans. A little side note, this k value is always positive. If you get a negative value here, you missed a negative or the math is wrong. More than likely you just missed the negative, but you might want to check your math again. This is also an important thing whenever you get to college and you start doing differential equations and you start solving for these values in kind of interesting ways. If you take a root of something, you'll get two answers, but you only want the positive answer for a spring constant because the spring has to physically exist. So that's something to keep in mind there as you go about into your later physics careers. Okay, so that's it. We're just setting up F equals ma, thinking about how an object moves. There's our spring force, there's ma, and from there it's just a substitution of kx, and we call it a day. So with that, this problem's finished. Take it easy.